When you look up at the night sky, there are thousands of stars staring back at you. But those are just a tiny fraction of the total number of stars in the universe. Our galaxy, the Milky Way, contains over 250 billion stars, and our nearest galactic neighbor, Andromeda, contains over 1 trillion stars. And those are just two of the some 200 billion galaxies in our universe. Now, when you put all those numbers together, it turns out there are about 1 billion trillion stars in our universe. And to put that number into context, for every grain of sand on the Earth's beaches and in the Earth's deserts, there are 10 stars in the universe. Now, every one of those stars is a sun. And over the past 25 years, astronomers have learned that each one of those stars, statistically speaking, hosts at least one planet. Now, that doesn't mean every star you see in the night sky has a planet orbiting it. Some have more. Our sun, for example, has 8 planets, or 9 if you live here in Flagstaff. And some will have none. But on average, there are more planets in the universe than there are stars. And so I believe that we are closer than ever to finding a planet with life on it that could host life and possibly even intelligent life. And I'm going to talk to you today about how we find those planets and how we characterize them. So while exoplanet science is a relatively new field, the idea of finding planets around other stars is not new. In 1952, an astronomer by the name of Otto Struve postulated that a large planet could be detected using modern techniques. However, it wasn't until the 1990s that the first planet orbiting a star like our sun was found. And indeed, some astronomers didn't believe that it would actually be possible to find planets. Looking for the light from a planet is like looking for the light from a firefly flying near a lighthouse. It's incredibly difficult to see. Stars shine millions to billions of times brighter than any planets. And so how, you might ask, do we actually find exoplanets? And so one way is by directly imaging them, by simply taking a photo of the star. Now, to do this, you have to block the light from the star to reveal the presence of a planet. And astronomers have developed a very clever piece of technology called a coronagraph. Now, a coronagraph blocks the light from the central star, revealing the presence of an orbiting planet. Now, here you're seeing over a decade's worth of observing on one of the world's largest telescopes to reveal the presence of 4 Jupiter-sized planets orbiting this star. Now, these planets are about the same size as Jupiter, but they orbit much further out than Jupiter does to our sun. And so this system is very unlike our own solar system. While directly imaging planets is very powerful, it's very expensive, and very few planets have been found this way. One of the most successful methods for finding exoplanets has been the radial velocity technique. This is a technique very near and dear to my own heart, and is one I use every day or every night while I'm observing at the telescope. And so the presence of a planet orbiting a star moves the center of gravity of the system radially outwards from the center of the star, causing both the star and the planet to do somewhat of a dance. And by measuring the Doppler motion of the system, we measure the light from the star moving towards us and away from us, blue shifting and red shifting. Now, the amplitude of this motion is directly proportional to the mass of the planet, and the periodicity of the signal is proportional to the orbital period of the planet, which in turn is proportional to the separation, the distance between the planet and the star. This is how the first exoplanet orbiting a main sequence star like our sun was found. The star, 51 Pegasi, hosts a planet, 51 Pegasi b, 51 Peg b for short. Now, this planet is incredibly special. Not only is it the first exoplanet detected, but it is also not like any planet we have in our solar system. Its mass is very similar to that of Jupiter, but it orbits its star in just 3 days. And to put that into context, the Earth orbits our sun once every 365 days. This planet is 10 times closer to its star than Mercury is to our sun. Its surface is heated to over 5,000 degrees, so really not a very pleasant place to go. But besides being the birth of exoplanet science, 51 Peg b also turned a very well-established field in astronomy on its head. You see, astronomers didn't have an idea of how this system formed until we discovered 51 Peg b most astronomers believe that all solar systems would look like ours. You would have rocky planets close to the star, gas giants further out. And so the detection of 51 Peg B completely turned this on its head. And astronomers have now been working very hard to come up with a new theory on how you can get such a large planet so close to its star. So while the radial velocity technique is a very powerful method for finding the mass of a planet, it's very time-consuming. It requires multiple observations of one single star at a time. So it's very slow. But so to come across that, astronomers have come up with a much cleverer technique, a new technique called the transit method. Now this method allows us to monitor thousands of stars all at once. And quite simply, all we do is we monitor the brightness of these stars, searching for a dip in light caused by the planet moving in front of its star, blocking a portion of the light as viewed from here on Earth. Now, the amplitude of the dip in light corresponds to the size of the planet's radius, and the time between the dips corresponds to the orbital period of the planet, just like in the radial velocity technique. Now, this technique was so successful from the ground, it caused NASA to dedicate an entire space mission to this search for transiting exoplanets. NASA's Kepler mission launched in 2009 and monitored the brightness of over 150,000 stars every 30 minutes for 4 years, and uncovered thousands of new exoplanets. Indeed, the follow-on spacecraft, NASA's Transiting Exoplanet Survey Satellite, TESS, launched just over 2 years ago, and is already finding thousands more planets. So there are no shortage of exoplanets for us to go and study. Now, these planets are incredible. They're completely diverse and very, very different to any we have in our solar system. You could go visit the lava oceans on 55 Cancri E. There are planets orbiting multiple stars. Kepler-16b is one of them. It orbits 2 stars. So imagine looking down and seeing you had 2 shadows, or looking up in the sky and seeing not 1 sun, but 2. How incredible would that be? One class of fascinating planet turns out to be very common, but we don't have them in our solar system. These are the super-Earths. These are planets slightly larger than the Earth, and so being slightly larger, they have a much heavier surface gravity, and so great for skydiving. Now, not all planets will orbit stars like our sun. The majority of stars are much smaller than our sun. These are called red dwarf stars, and they make up about 70% of the stars in our stellar neighborhood. And so a planet orbiting one of those stars will have a very different type of atmosphere. It will have very different conditions. Kepler-186 is one of those stars, one of those planets. Its grass is likely to be red because that's where the energy from the star's light peaks. Notice how I've said how many of these planets are extreme. They're different. They're not like the Earth. So we found thousands of planets, but we've yet to find a true Earth twin. We're yet to find a planet the same size as the Earth, orbiting a star like our sun, at a distance the same as the Earth's distance from the sun. And the reason for that is not that these planets don't exist, it's that it's a very hard measurement to make. And so while astronomers are constantly searching for habitable planets, it's worth thinking about, well, what makes a planet habitable? Why are we focused on this search for an Earth twin? Now, when you're thinking about whether a planet is habitable or not, it can seem overwhelming. We've got thousands of possible candidates. How do we know which one to invest possibly hundreds of hours of telescope time into to try and determine if it's habitable or not? And one of my colleagues actually put how we're searching for habitable planets really well. She said, go and search. What if I told you, go and search for a dog? You'd probably go outside and you'd look for something with 4 legs, something furry, probably incredibly cute, something like Milo. This is one of my good friend's dogs. He comes and sits in my office while I'm searching for exoplanets. But if I told you to go and search for not a dog, what would you do? Where would you start with that search? So astronomers are trying to search for plant signatures that make life like we know it here on Earth. And so the search is kind of, if you were on a distant planet looking at the Earth, what would you be looking for? How would you see the Earth and determine it was habitable? And the first place to start is the size of the planet, whether it's a small rock or a large gas giant. And so we get the mass of a planet from the radial velocity technique, and we get the size from the transit technique. And combining them together, we get the density of the planet. And so we know, is the planet a rock that has a surface that could potentially hold water and have life walking around on it? Or is it a large gas giant like Jupiter and Saturn, which are very unlikely to host life? The next step is knowing whether the surface temperature of the planet is right for life to exist. And we do this by searching for the temperature where liquid water can exist on the planet's surface. And so stars irradiate heat that heat the planet up. And so if you're located too close to the star, like Mercury and Venus in our solar system, then the planet is likely too hot, water will evaporate. Similarly, if you're too far away from the star, it's too cold. The water will freeze and become ice. You need to be located in what we call the Goldilocks zone, the habitable zone, where liquid water can exist on the surface of the star. Now, the habitable zone is very much a function of the host star itself. Larger stars produce more radiation, so the habitable zone is further away from the star than it is around our sun. If the star is much smaller than our sun, then the habitable zone is closer in because the star is exhibiting less light, less irradiation. One example of a system where this is the case is the Kepler-186 system. Now, this system hosts 5 planets. One, Kepler-186f, is very similar in size to that of the Earth. But the star is about half the mass of the sun. And so the habitable zone is about the same distance as Mercury is from our sun. Now, Mercury is not habitable, it's too hot, but around this smaller star, Kepler-186f is actually in the habitable zone of its star. Now, Kepler-186f, while a really interesting target for potential habitability studies, cannot be called an Earth twin. And that's simply because the star is much smaller, and so it is not like our sun. And astronomers don't fully understand yet the consequences of living around a star that is not like our sun. And indeed, we found thousands of planets, but none quite like the Earth. And so here you're seeing the separation from the star, how far the planet is from the star versus the mass of the planet. And you'll note there's no points on this diagram around where the Earth is. Now, that's not because the planets themselves don't exist. It's that all our techniques to find them are biased towards finding planets very close to their star and that are very large. And so finding a planet like the Earth is incredibly difficult. But that doesn't mean we're not trying. And so I'm part of a team that has actually built an instrument we believe is capable of finding an Earth-sized planet orbiting a star like our sun. And so to give you an idea of how difficult a measurement that is to make, if you were on a distant exoplanet looking to find planets in our solar system, you'd have to be able to measure the sun's Doppler motion by about 10 meters per second to find Jupiter. And to find Earth, you'd have to measure it at 10 centimeters per second. Now, to put that into perspective, I did some research before this presentation, and I learned that the world record for the speediest tortoise on Earth is held by Bertie, and he moves at 28 centimeters per second. So you have to be able to measure the star's motion 3 times slower than the world's fastest tortoise. So it's quite the endeavor. But our astronomers at Lowell Observatory have teamed up with astronomers from Yale University, and we've built the Extreme Precision Spectrograph, which has now been installed on Lowell's 4.3 meter Discovery telescope. Now, this instrument is world-renowned. It is brand new, it is cutting edge, and it uses technology never before seen to ensure that we get the best data and are able to find a planet like the Earth orbiting a star like our sun. Now, this won't be a quick mission. To truly characterize and find a planet like the Earth, you have to trace out its whole orbital curve, which for planets like the Earth can take years. And so this will be a very long-term project, but we're confident that this instrument, paired with our telescope, will be able to find a planet like the Earth in our lifetime. Now, instrumentation is just one side of the argument here. We've checked off, we have a brand new instrument capable of making the measurements necessary. But we also have to deal with other things stopping us from finding this planet. And that is from the star itself. So stars are not simply static light bulbs. They don't just exhibit a constant amount of light. I'm sure many of you have maybe looked through a telescope up at Lowell Observatory at the sun through a solar filter, and you've seen spots on the surface of the sun. You've seen maybe faculae and plage, these bright, dynamic regions that constantly change the light coming from the sun. And those can act to drown out any signal from an orbiting planet. And astronomers are now starting to get better and better at understanding how these astrophysical noise sources impact our ability to find exoplanets, small exoplanets like the Earth. And so what we've done is we've realized that, well, our telescope at night is very busy searching for exoplanets. During the day, it sits idle. But we have access to one incredible star, our sun. And it's very close to us, so we can get great data on our sun. We can get these wonderful resolved images of our sun at all sorts of wavelengths. And so over the past year, I've set about to build a telescope that will send sunlight into Express, our spectrograph, just like we observe stars at night, to build up one of the world's largest and best data sets of sun as a star observations. And so it's not a big telescope. The sun is very close to us. Our solar telescope is here in the front of this image. It's about 70 millimeters in diameter. It's the size of a good camera lens. And it sends sunlight into Express for 8 hours a day on every clear day we have here in northern Arizona. And we believe that by building this data set, we'll be able to better understand how we can quantify the impact of noise in our spectra and tease out the signal from a tiny orbiting Earth planet. I'm very excited to show our first light spectrum of the sun. We observed this a few weeks ago. Here you can see all the incredible data we take of the sun with Express. You're seeing the blue part of the spectrum all the way through to the red part of the spectrum, just like your eyes would see. And each one of these vertical black lines is a feature in the sun's atmosphere. And we use these features to calibrate our data and determine the noise, the radial velocity of the sun. And so by having this incredible wide wavelength solution provided by Express, we're able to get really, really precise measurements. And so next time you go outside, I hope you'll take a look up and think about all the exoplanets that you're looking at when you see the stars in the night sky. And I hope I've convinced you that, yes, the Earth is unique, it's special, but I don't believe it's the only place that hosts life in the universe. The universe is simply too big for us to be the only place with intelligent life on it. And I believe that we are closer than ever with instruments like Express and Lowell Observatory's telescope. We're closer than ever to being able to find a planet like our Earth that is potentially habitable, and we can begin really quantifying whether a planet like that is habitable or not. Thank you.